Welcome back to the Math Professors, where we cover subjects in algebra, statistics, calculus sequence, and so on. So if you like the free videos and you want us to grow our channel, please consider liking, subscribing, and sharing. So today I'm going to do an area of a region using double integration. So the definition is the area enclosed by a plane of region R is defined by A, which is going to be equal to the double integral over the region with respect to the area. So just a quick graph of what I'm kind of talking about as we're talking about this plane region, and we have, this area is kind of bounded by these two curves, though it doesn't have to be, connecting two curves, and I'll show you a couple examples. But really, we can say, from A to B, and then say from one curve to another curve. So I'll come up with an example, and I'll show you how this works in practice. So here's an example. Find the area bounded of the region enclosed by the curve y equals x and y equals x squared. And a lot of times it helps to draw this picture. So I'll draw this picture. So I'll do it over here. So what we're going to have is we're going to have the curve y equals x. And then we're also going to have the curve y equals x squared. So it's going to look something like this. Now, it should be symmetric, so forgive me, I'm just going to erase that part of it, because really we can see that the spot that's going to be enclosed is going to be right here. So we're trying to find, this pink area. Now I know by definition, this thing's area is equal to the double integral over the region with respect to that, to that area. So really we just have to define R, and then we're going to have to integrate it, and we have some choices here. It depends on how we want to integrate this thing. Do I want to integrate it with a vertical scalar bar? Do I want to integrate it with the horizontal scalar bar? And well, let's just start out with something horizontal, because vertical. We tend to do this in, say, a Calc 1 class. We tend to integrate most things in this direction first. So our region of integration for this R, we have to know where is this thing going to start and where is this thing going to end. What is essentially your A and what is your B. So in order to find that, we really have to find the intersection of these two curves. I have y equals x and y equals x squared for this one. And we know their intersections happen when these things are equal. So this is when x squared is equal to x. And what I could do is, since this is quadratic, we want to set it equal to 0 so then we can factor. Avoid dividing both sides by x, because what you do is you lose one of your solutions. If you divide both sides by x, you'll get x is equal to 1, which is one of the solutions. But you also lose that x equals 0 because you've changed the domain of your solution. So we can see that we have x equals 0 and x equals 1. So we can tell that this is going to intersect at 0, this is going to intersect at 1, or more importantly, 0 is less than or equal to x, less than or equal to 1. So that's the bounds on x. Now the dots, or the vertical bounds, these are going to be the ones connected to the curve. So this bound right here and this bound right here. Well, the lower bound is going to be this x squared. So we're going to have y is going to be bounded between this dot, which is going to be on the x squared curve, and then this dot, which is going to be on the x curve. So when I set up this iterated double integral, this is going to be the integral from well, actually, let's talk about how we start this. So, d what, d what. So if you're integrating in this direction, this is going to be your, I say it's your start and your stop. These are going to be your end places. This is going to be your 0, and this is going to be your 1, and this is going to be dx. So, the outer part's going to be the direction which you're integrating, and the inner part's going to be your bottom and your top, or your minimum and maximum of the region. So this is going to be x squared to x. And this is going to be with respect to y. All right. Now, the reason why this is the area is because usually you'd see a double integral being a volume, but what we have is a function that's equal to 1. So really, we technically have a volume with a height of 1. So, length times width times 1 is still going to give you the same thing as length times width. So the integral of 1 with respect to y is going to be equal to y. So this is going to be equal to the integral from 0 to 1 of y evaluated from the lower to the upper dx. So we'll evaluate this at top minus bottom. So this is 0 to 1. This is x minus x squared dx. Now we can integrate this thing with respect to x next. So I'm going to erase this slightly so if I want some room. I want to do it in the other direction, and I want to see it all together. So this is going to be x squared over 2 minus x cubed over 3, evaluated from 0 to 1. And, plugging in 1, this is, 1 squared over 2 minus 1 cubed over 3 minus 0 squared over 2 minus 0 cubed over 3. So we can see that's going to be 0. So 1/2 minus 1/3 is going to be equal to 1/6. So 3/6 minus 2/6 is 1/6. All right. Now, Fubini's theorem says that we can, change the order of integration, but we have to be careful of our bounds here. So really what I mean by that is you can integrate, with a vertical scalar bar, or you can integrate with a horizontal scalar bar. So let's draw that over here because I have a little bit more room. So if I want to do the exact same picture, I want to do this with a horizontal scalar bar instead. So this is the first curve, the second curve. Now, when you want to integrate this with this horizontal scalar bar, we're going to have to do it this way. So now I need to know, where does it stop, where does it end? In, in that y direction. So what we can see for this particular part, I'm going to put the area here. If I want to do it this way, the area can be found by the double integral of the start and stop with respect to y this time, and the integral of your minimum and your maximum bounds, or your left and right, and this is going to be dx. Okay, so let's figure out where we start and stop. Now we do actually kind of know some solution points. I know x is equal to 0. I've already found their intersection. So this is the point x is equal to 0. And when you plug it back into any one of these two functions, when x is equal to 0, y is equal to 0. So really, this right here is the point 0, 0. And then similar here, when you plug x equal 1 back into any one of these things, you can see that this is the point 1, 1. So, for the x values, I went 0 to 1 on the x coordinates. Now for the y values, if I'm going to do start and stop, it's going to be, this 0 and this 1. It's technically not the same coordinates, so just be careful. They happen to be the same numbers, but they're not really the same numbers. So y is going to be bounded between, 0 and 1. And now I have to figure out, the left and right bounds of this thing. Like, what about this piece right here? And what about this piece right here? So since these are now x values, I have to solve, these equations for x. So, this is equal to x equals y. And then this one is going to be x is equal to plus or minus the square root of y. But since I'm in the first quadrant, it's just going to be positive the square root of y. So x is going to be equal to positive root y. So now that means this is the smaller one because it's it's less, it's to the left, and this is the bigger one, it's right. So it's going to be this is going to be your lower, which is y, and this is going to be your upper, which is root y. Now again, this is still just a 1 here. So the integral of 1 dy is going to be, dx is going to be x. So this is the integral from 0 to 1 of x evaluated at the bounds, dy. So evaluate, plug in the top, plug in the bottom. So this is the integral from 0 to 1 of root y minus y dy. And now I'm going to plug in 1, plug in 0. Oh, I got to integrate first. Now I have to integrate, then I can plug in 1, plug in 0. So the integral of y to the 1/2 minus y dy is going to be y to the 3/2 divided by 3/2, or 2/3 y to the 3/2 minus y squared over 2 evaluated from 0 to 1. Should get all the same values, and I do. So plugging in 1, this is going to be 2/3 times 1 to the 3/2 minus 1 squared over 2, and then when we plug in 0, this is 2/3 times 0 to the 3/2 minus 0 squared over 2. Again, that is 0. So this is going to be 2/3 minus 1/2, which is going to be 1/6 again. Now, what's really interesting about this is again, it doesn't matter the order in which you integrate. You get the same, area in both cases. So let's do one more setup and show you sometimes it's easier to integrate in one direction than it is the other. All right, here's going to be our last example. So find the area enclosed by y equals 1 minus x, y equals 2, and area enclosed by y equals 1 minus x, y equals 2, and y equals e to the x. And again, it's useful to be able to draw these things so you can see how you want to integrate this. All right, so let's set up 1 minus x, slope of -1, y-intercept of 1, so it's going to look something like this. Y equals 2, and then y equals e to the x. Maybe I should make it look more exponential. Boom, there you go. So y is equal to e to the x. Now we're going to have to decide, how we want to integrate this thing. Do I want to use vertical scanner bars or do I want to use horizontal scanner bars? And let's just look at the vertical first. Now, if I do a vertical scanner bar, if I start here and here, we can see that as I move from this triangle area to this, well, still triangular, but a exponential bottom to this, what I can see, if I want to do this, I'm going to have to do two double integrals. I'm going to have to integrate from, whatever this x value is to 0, and then 0 likely to whatever, this value is. So I'm going to actually have to set up the sum of two double integrals. However, if we decide to integrate with respect to, with horizontal scanner bars as opposed to vertical scanner bars, we do it this way. You can see no matter where I am in the region, this dot lives on this curve and this dot lives on this curve. So we're going to do it this way, so I only have to do a single double integral. So that means my area is going to be equal to the double integral. Let's talk about what the bounds are going to be here, and actually what variable I'm going to integrate from the outside first. So since this is sliding up, I know that my last variable is going to be dy because this is going to go. This is sliding up. So let's find the start and the stop. Well, the start and the stop is going to be whatever this value is, of course, of this value. So I can tell that this is going to be 2. And I also know that this is equal to 1, but just in case we don't know that, what I'm going to do is I'm just going to intersect, these two curves. So I have y is equal to e to the x, and I'm going to set that thing equal to y is equal to 1 minus x. So 1 minus x. Okay, let me pause this to make sure I don't make a mistake. This is when these two things intersect. So when this is 0, this is 1. When this is 0, this is 1. So this has a solution of x is equal to 0. Now if I want to find the y value, which is what I'm more worried about, I'm going to have to plug 0 back into any one of these. So y would be equal to 1 minus 0, so y would be equal to 1 in this case. So which is what I'm more worried about, I'm going to have to plug 0 back into any one of these. So y would be equal to 1 minus 0, so y would be equal to 1 in this case. So I can tell that that is 1. So this goes from 1 to 2. Now, when I want to figure out what this left dot is, the minimum to the maximum bounds here for your x's, I'm going to have to solve these curves for x. So, solving this curve for x, let's just switch. So x is going to be equal to 1 minus y. And then similar here, if I want to solve this one for x, I'm going to have to natural log both sides. So x is equal to the natural log of y. All right, so setting this up, this is the smaller, the more left. So this is going to be 1 minus y, and this is going to be equal to the natural log of y. Now we integrate. So the integral from 1 to 2 of 1, this is just going to be y evaluated at the bounds. Once you get kind of good at this, if this is just 1, it's just going to be this function minus this function. So this is going to be the integral from 1 to 2 of the natural log of y minus, be careful of this, it's subtraction of the entire thing. So this is going to be minus 1 plus y dy. Let's just do that now. So distributing that is going to make it a plus. And now I can integrate these things. So we know that the integral of the natural log of y is done by parts. So this is going to be equal to y natural log of y minus y. And just a little side note for you, if you want to integrate this thing dy, you're going to have to make your u the natural log of y, and then your v equal to dy. So then du is going to be equal to 1 over y, and dv is going to be equal to y. And then when you set this up, you can see u, this should be dv, and you can see that uv, which is equal to this, minus the integral of v du, but you know this multiplication is just going to be 1, and the integral of 1 is going to be y, so that's where that comes from. Now minus 1, which is going to be the integral of that, which is going to be y, and then this is going to be plus y squared over 2. Now we're going to have to integrate this from 1 to 2. And to save yourself some time, I will just evaluate it. So plug it in 2, and then plug it in 1, and then simplify, and this is a result. So the goal of this last example is to show you that integrating in a particular direction sometimes is easier than, say, another one. So that's what I have. Thank you. Please consider liking, subscribing, and sharing.